Let's get started. So, welcome everyone to the first of the Orbital Materials Seminar Series. My name is Mark Neumann, and I'm the Head of Machine Learning at Orbital. And we've organized this kind of seminar series around some of the ideas we've been using extensively for developing our force field that we released over the last couple of months. Jonathan and Marcel have been, some of their research has been key for the modeling ideas and the data that we've been using internally at Orbital for the models. So we wanted to get kind of an opportunity for people whose work has been influential to us to kind of speak publicly about the research and kind of gather a group of computational material scientists to kind of see where we think the future of kind of computational material science, particularly around neural network potentials, is kind of going. So that's the kind of motivation for this seminar series, and I hope you enjoy the talks. Just admit another batch of people, and then we'll get going. Okay, so for the first talk, I'd like to introduce Marcel. Marcel Lange is a postdoctoral researcher at the Cosmo Lab at EPFL, where he develops machine learning models for material science, particularly focusing on long-range interactions and the significance of symmetry in machine learning neural network potentials. So today he's going to talk about breaking rotational symmetry in machine learning potentials and how that affects atomic scale modeling. Yeah, we hope you enjoy.
All right, wonderful. Thank you, Mark. I'll take control if I can. All right. I think we can skip this slide, I guess.
Yeah.
Oh, this. All right, here we go. Thanks for the introduction. I'm Marcel. As Mark already mentioned, I'm a postdoc at EPFL. And today I'm presenting some work together with two colleagues, with Sergey and our PI, Michele, where we really wanted to just check how much unconstraining in machine learning models we can get away with in practice. Yeah, this paper just came out, so this is rather new, and I'll walk you through it in the next 25 minutes. So to set the stage a little bit, wait, I think spacebar doesn't work. All right, to set the stage a little bit, the general setting that we're always working in is one of trying to learn a structure property mapping with machine learning models, where our underlying sort of ground truth structure property mapping is something like density functional theory. And usually the property that we're trying to predict, at least in the context of machine learning and atomic potentials, is the potential energy, and then the derivatives of the potential energy that give the forces and the virial or the stress, which is what actually drives dynamics simulations. The interesting thing about this modeling problem is that it is not completely generic. It's not completely without structure. And in particular, we know something about the target that we're trying to fit. We know that it has certain symmetries or invariances with respect to certain transformations. In the case of the potential energy, this is permutational, rotational, and translational symmetry. So permutational symmetry simply means that if we change the order in which we write down the atoms in our system, the energy doesn't change because this is essentially just arbitrary labeling. Rotation, of course, means that if we perform a global rotation of the coordinate frame, so we rotate all the positions, or for example, all the vectors connecting all the atoms, our potential energy also doesn't change. And finally, if we do a global shift of the coordinate system, we also don't change the potential energy. So this is translational symmetry. And for many years, I think essentially since the inception of this modern concept of machine learning potentials, the received wisdom and the sort of general empirical consensus was that it is essential to put these symmetries by construction into the machine learning models that one is trying to build. And let's briefly review how people do this in practice. Permutation and translation are, I would say, slightly more straightforward in this case. because essentially what you do is you go into this idea of introducing a cutoff radius. So you make a finite range approximation for your interactions. Then inside of these atomic neighborhoods, you construct the displacement vector, so just the vectors connecting the central atom with each neighbor atom. This gives you, by construction, already translational symmetry, because you've sort of gotten rid of any absolute coordinates. And then permutational symmetry you simply get by doing all your aggregations across neighborhoods in a commutative way, so usually by summing up or taking the mean or something like this. This takes care of these two symmetries. Rotation, on the other hand, is slightly more difficult in some sense. And here I think there are two paths that sort of the community has taken. The first of which is the more historically trodden one, is just working with invariant features in the first place. So one puts distances into the model, or maybe angles, dihedral angles, or slightly more, in a slightly more sophisticated way, something like slope descriptors. So something that is by construction already invariant to rotations, and of course to the other symmetries as well. And then the model doesn't need to worry about symmetry at all, because it's already working on featurization that has the symmetry. There's, however, another path that is, I would say, has more emerged in the last couple of years together with the rise of geometric deep learning, where we work with equivariant internal features. So we say that our internal features of the model have geometric meaning. So they're not just arrays of numbers, they're arrays of numbers that transform in certain ways under rotations. And if we construct our model carefully to respect this transformation behavior, to preserve it across all the layers, we have what's called an equivariant neural network. And then at the end, for predicting a scalar quantity, we typically then reduce these equivariant features back to a scalar and predict something like the energy. This is all very elegant and mathematically exciting. However, doing this in practice is a fairly severe restriction on sort of the model design space that you're allowed to explore, because making sure that all these transformations are preserved over the entire network means that the toolbox of deep learning that one usually has at one's disposal is limited. For example, there's only very limited amounts of nonlinearity one can access. Features need to be mixed in very specific ways to preserve equivariance and so on. And this often also requires operations that can often be made efficient, but it is not very trivial to do so. And it is actually a big bottleneck in implementing these models sometimes. And also, of course, there is some implications for the optimization landscape that you're working in and so on, by restricting your model class to this very specific subset of models. So with this in mind, and sort of everyone over and over again realizing the sort of bitter lesson of deep learning, that things that scale are often better than things that are clever, there has been a renewed and, I would say, new interest in unconstrained models in this domain, where unconstrained just means that your model deliberately ignores some symmetry at the level of the architecture and instead learns to approximate the symmetry in the learning process. This idea, I think, has arrived much earlier in other parts of machine learning, for example, learning on point clouds, where most of the state-of-the-art models, I think, are not invariant. This came into our community, I would say, also a few years ago already, but I feel like this year, this whole discussion has exploded somewhat. I think also on the tail end of AlphaFold 3, somewhat famously dropping equivariance from their model. Then we, of course, just in the last couple of weeks, we have the release of Orb, which is non-invariant as far as I know, and also Escape, and of course PET last year, which is the model that we're using today. So this was an interesting topic. All right, let's get back to what these models are. As I said, these models learn symmetries, and in particular, they learn from the data, which was of course generated with a process that has these symmetries. And this learning is typically enhanced with data augmentation. So at training time, we apply some random symmetry transformation to the inputs over and over again to make the model learn that it has to respect certain symmetries. Empirically, from all of these papers, we know that these models are rather good at beating benchmarks. So they're often state-of-the-art. But we know also that benchmarks don't always tell the whole story. There's always the question of how do these models actually perform in simulations, and is there actually a price to pay in practice for breaking the symmetries, even if it makes you have a model that's good at fitting something. And this is what we wanted to explore in our paper. In particular, sort of our mission statement was this, that we wanted to see the impact of having a non-invariant model, non-invariant with respect to rotations in this case, when used as a machine learning interatomic potential for water. And I'll now briefly walk through sort of this mission and all the different parts that made this paper. So first, we need a model that is has these properties that I just described. In this case, the model we're using is called point edge transformer, PET. It is a rather sophisticated diagram here, but in its essence, this is just a relatively vanilla transformer that's acting on edge features within neighborhoods, and just performs attention within every neighborhood, mixes the features with their reverse features in other neighborhoods, and that's essentially it. And the relevant part for today is if you look into this architecture diagram in this box that I have drawn in red, you see that into the edge featurization, we put the displacement vector Rij, and this just gets put into a multi-layer perceptron. And at this point, we broke rotational invariance because we have stopped sort of labeling this area of number that comes out with any geometric meaning. It is just an area of numbers that has no particularly well-defined rotational transformation. It's just numbers. So this transformer is no longer rotational invariant. By construction, however, it's still invariant to permutation and translation. So we really focus on translations, on rotations today. So this is our model. The next thing we need something to compare against. So we need a reasonable approximation of an invariant ground truth. And for practical reasons, because it is rather complicated to compare two models already, we wanted to take the same model and symmetrize it at inference time in order to have some sort of comparison. And here what we chose to do in the end is to just make a grid of all the Euler angles with some quadrature weights, and then evaluate the model for each of these transformations and take the average. And this gives us an approximately invariant model at the end. The actual grid that we're using here has 18 rotations and then inversions, so 36 total transformations. For sort of technical reasons, this is called 2i, but we don't need to worry about it too much. So now we have the PET model that we're using. We have a way to sort of symmetrize it to test things. The last thing we need is data set and actual building the actual model. So we used a bulk water data set from Bingqing Chen from a few years ago. This is around 1,500 samples with 192 atoms. And we just train for a few days on a V100, this PET model, with data augmentation at every epoch. So essentially every sample is always randomly rotated every time it appears in the training process. So this data augmentation is essentially free because we don't increase the size of the data sets. The data set, we just sort of opportunistically do it every time we're already loading the data. So that's it. If you look at this table, unfortunately, I don't have a pointer. You can just look at the bottom 3 rows of this table. You see that this model is competitive, for example, with NeckQuip, and it is really very satisfyingly good on this data set. Now that we have a model, the next thing we can do is we can look at how much of the error is actually due to non-invariance. So we just compare the predictions of the model with its own averaged version, and you see that in domain, so on the test set or even on like some other bulk data, this rotational error is rather low when compared to sort of the overall errors of the model. However, what is somewhat interesting to note is that on the gas phase, so out of domain and extrapolation, the rotational error is actually quite significant. So this is interesting to keep in mind. I will take a sip of water and then we continue. So now, being the academics that we are, of course, looking at this and seeing that out of domain is the most difficult, we of course started immediately with out of domain experiments of simulating a single water molecule in vacuum with a model that was only trained on bulk water. And the first thing we did was just doing velocity Vallée NVE simulations and just looking at the trajectories. And in particular, what we looked at is the angular momentum. So here on this plot, you see the red lines is the unaveraged raw model that we're working with. And you can see that the components of the angular momentum are slowly precessing. So it's a bit like a spinning top that you've given some hit and it starts somehow spinning. Whereas the average model, just everything is conserved and there's no movement in the angular momentum. This is, of course, because there's a non-zero torque acting on the non-average model. We can see here in this little inset plot that at no averaging, there's quite a significant torque that goes systematically down if we increase the density of the averaging grid. And of course, all of this in the end is a consequence of Noether's theorem. So what we have done here is we've broken a symmetry, rotational symmetry, and every symmetry has associated conserved quantities. The associated conserved quantity for rotational invariance is angular momentum. And so if you break angular momentum, if you break rotational symmetry, you break the conservation of angular momentum. And this you will see here in the fact that the components of the angular momentum change, and also the total angular momentum starts slightly oscillating. So there is no escaping physics. This was the first check. There is a clear signature that we have broken a symmetry. But of course, the question is, how much does this matter in practice? So the next thing we did is we took the same water molecule and now do simulations at fixed temperature at 300 Kelvin and just let it run for a long time. And then we made a histogram of the sort of absolute orientation of the water molecules over time, or rather the single water molecule over time, by just defining a vector sort of in the middle of the hydrogens and then plotting this histogram on the two angles that characterize this vector. This is these maps that you see here. And you see that for the original unaveraged model, there's a clear sort of preferential orientation that it has over these 10 nanoseconds of MD. So there is an anisotropy in our system now because we have this, because we've broken this rotational symmetry. And this is clearly a signature of this broken symmetry. Whereas for the sort of average model, it's absolutely flat. There is no preferred orientation, and all you can see in this plot is a little bit of statistical noise that's much below a few standard deviations. It's just because we didn't run 100 nanoseconds and only 10. But we see that also in this case of thermostatic dynamics, there is still some sort of spurious anisotropy in our system. So we can conclude that in this extrapolative regime, this very strict case of a single water molecule, we actually notice this lack of invariance. However, not everyone is looking at a single water molecule, and indeed we trained it on bulk water. So the next experiments are on bulk water. And here we find, rather interestingly, that there is absolutely no impact of this non-invariance. So here we see the same plot from previously, just for the bulk, so averaged over all the atoms in over all the molecules. And it's completely flat. There is no preferred orientation to any statistical measure you want to impose. Encouraged by this, we then started looking at other observables that we could think of for water. So here we have the radial distribution function and sort of the correlation for a given distance between neighboring between the orientations of different neighboring water molecules. Here you see also no difference between the non-invariant and invariant model. The same holds for dynamical correlations. So at the top here, you see the mean squared deviation. So the slope of this curve would give the diffusion coefficient. It's also unchanged. At the bottom, we see the dipole autocorrelation function. It also has not changed. So for this liquid water, we could find no observable where this non-invariance made any difference. So now we had in our mind, okay, we have a single water molecule, very, very deep extrapolative regime, very problematic. With bulk, we see nothing. So the next thing we did, we checked another bulk system, but not liquid, instead frozen water, so hexagonal ice. Here the task is to take these proton disorder geometries from this paper and just relax them, so putting the hydrogens in the right place. And here also there's very, very little impact of non-invariance. So the final relaxed geometries are very similar. The force error on the starting geometries, which would determine where this optimization goes, is on the order of 0.1% of the total force. The energy difference between the different ground states, which is already on the order of a few fractions of a millielectron volt per molecule. Here the error is an order of magnitude less. So everything is rather unproblematic in this case, even though this is somewhat out of domain, being frozen and not liquid water. So we can conclude for this in the bulk regime, and so the sort of more interpolative regime, there's essentially no impact that we could observe of dropping rotation invariance from our model, which for me was a rather surprising result. I got into this project to prove that physics is king and that you can never get away with breaking a symmetry. And indeed, I had to admit that for this particular case, I was wrong, and you can get away with it. But of course, it's not always clear what one can get away with in practice. And so for the last little bit, I just wanted to talk a bit about how to check these things in practice and how to sort of, if you have a computer in real life that's maybe not so big, this is our ISA cluster here at EPFL, how to do this in a reasonable way without breaking the bank. So let me briefly review the tools. So what we used here in this paper, what is sort of the most obvious and reasonable way to do things, is we just compare the predictions of our non-averaged model, of our unconstrained model, with its own predictions, but averaged over a grid. For example, here, grid of rotations. Here, the computational cost is very obvious. It is just proportional to the number of grid points. In our case, we have 36 points on the grid, so it's a 36-fold computational overhead, which is manageable, but still rather painful even for machine learning potentials. There are, of course, other approaches that are even more exact. So, for example, the ECSE approach that was sort of introduced together with the PET model in 2023. Here, the idea is that one attaches sort of coordinate frames to every neighbor in every neighborhood and then smoothly transitions between them and takes the average. This costs with every neighbor. So the computational cost is proportional to the number of neighbors. And the difficulty and the reason why we didn't use it for this paper is that you need to take into account all neighbors, including the ones that are only seen sort of implicitly via message passing. So this leads to very large effective cutoff radiuses and very large computational cost. But this would be a very useful tool, for example, for an Allegro-style local model, where one just has finite neighborhoods or small neighborhoods. In either case, what we found when you have one symmetrization procedure like this, that's rather expensive, what's useful in practice is to just do multiple time stepping with this method. So let the dynamics run with the unconstrained model for some time steps, for example, 10. And then every 10th time step, compute the full averaged model, and then correct the dynamics with this actual symmetrized model. If this is still too expensive, another thing that we played around with is that one could do essentially the same thing one does with data augmentation, but at inference time. So at every step of the molecular dynamics, one applies a random rotation to the inputs. So that on average, you have averaged over all the possible rotations. Both of these methods, of course, introduce noise. So they make your forces non-conservative, and that means that there is a drift in the total energy of the system. Here we have half a nanosecond of, I think, bulk MD. And we see on the y-axis the accumulated sort of drift in the total energy. So that's the total energy plus the energy that sort of gets dumped into the thermostat. And you see that it starts drifting, especially with multiple time stepping or random rotations at every time step, but it's not so terrible. And this is an amount of drift that one can very easily control with even a relatively mild global thermostat. So for thermostat at molecular dynamics, one can just do tricks like this to reduce the computational cost of averaging to something manageable, to do proper testing of the impact of non-invariance in practice. Okay, this brings me to the end of my talk. So just to summarize our results, we found for bulk water, so in this case that we studied, learning your rotational symmetry from data with data augmentation instead of baking it into the model seems to be perfectly fine. We could not find anything wrong with this. In the gas phase, you can see the consequences of this symmetry breaking, but nevertheless, you can run stable dynamics and you can control this via averaging. So in practice, I think for me, the takeaway is that things are pretty good in these models, so they can be made practical, and so this is an encouragement for everyone, and people have already started doing this. I mean, Orbital Material has been working on this model for quite some time to explore this design space of unconstrained models and see how far you can get with this. But of course, if one has a particular problem that one is studying, I think it's always a good idea to do sanity checking and checking that this unconstraining has not broken anything fundamental. And one way to do this, as I've shown, is averaging, comparing with an averaged model. This is functionality that we're integrating, for example, in IPy, which is an ND code that the lab is developing. But in general, this is also not a particularly difficult thing to implement in any given model. Finally, if we get some time for discussion, I'm personally very interested in finding out more about the sort of engineering trade-offs as opposed to the physics trade-offs in these models, because one needs, I think, a good reason to bother with all of this unconstrained model business. And for me, the trade-offs between having a fast equivariant model and a fast non-equivariant model, they're not quite clear yet. So I think I would rather enjoy learning a bit more about this. And of course, we've now checked one system in this paper, and there are for sure many more to look into to see how general this finding is. All right, that's the DOI of the paper. It just came out in MLST. The other thing is just the website for the paper, where we link all the input scripts for the MD, and where soon we will also link a tutorial introduction on how to run these sort of averaged simulations with IPy. All right.
Great.
I think we're ready to discuss. Thanks.
Yeah. So have a quick couple of minutes for questions. So if anyone has
also, I wanted to thank my co-authors and our
of course, yeah.
links.
Yeah, if you have questions, if you want to just, I think people should be able to access the chat. So if you want to just ask them in the chat, that will work nicely. We'll just do a few quick questions now because we slightly ran over. So unless people can't, I think people can access the chat, right?
Not sure. You can also always find me on Twitter if you have any further questions that we don't get to.
Yeah.
Looks like Johannes has a question.
Yeah.
Who's doing the? Are you calling the people, Mark?
Yeah. Cool. So let's start with Johannes. So, what is the actual performance advantage of the PET model over, say, NeQuip?
So the honest answer is that there is none at this point. I think, but I mean, this is what I alluded to in my last sort of comment. I think fundamentally these models should be possible to be made quite a bit faster, because basically you can drop all the complicated stuff of like doing Clebsch-Gordon contraction and doing very sparse matrix products. You can instead do basically vanilla attention, flash attention, whatever you want to do. But this is an engineering project that we have not yet undertaken. So at the moment, there is, for this particular model, I think a very limited computational performance advantage.
Nice.
This is the state.
Cool. So we've now got a question from Alex Moriarty. Do you think these results raise questions about the validity of these models for heterogeneous systems?
Heterogeneous in what sense? Do you know?
Yeah, good question. Where composition might affect preferential orientations like phase transitions.
I think it's an interesting thing that we need to look at. I think phase transitions would be a good indicator of broken things in the physics. I think we chose a relatively benign example with this water at a fixed temperature.
Yep. Arthur is asking, what's your take on Taco Cohen's recent paper? I think you probably know which one we're talking about, but
Yeah, I mean, I don't know if everyone else knows, but there was a paper recently from Taco Cohen's group where they basically checked like an equivariant and non-equivariant transformer at I think they did basically like scale experiments, so scaling up to large data sets and so on. And they found that at every scale, equivariance is better, which is, of course, as a physicist, makes me happy. But we will see. I think this always depends, I think, very much on the particular model in question. I think it's hard to make general statements about this. Very complicated model in science space.
I think people interested in this question should also check out our last seminar series in this series with Aditi and Yilun, who will be talking about their different. They have two kind of slightly contrasting approaches to scaling these models, and it kind of Aditi's escape paper kind of addresses the almost the opposite question or takes the opposite stance from Taco Cohen's recent group. So I'd recommend people read that. Cool. Okay, I think let's get started with Jonathan's talk. Otherwise, we're going to run over. So yeah, thanks, Marcel. That was a great talk. And if
so
people
all the
have
other questions, I think you can, if you have Twitter, you can write me at marcel.sci, all one word, or you can just write me an email at my name at epfl.ch. Nice. I think it should be linked in the event description and so on.
Yeah,
it should be easy to reach me somehow.
Yeah. Cool. So our next talk is from Jonathan Schmidt, who is a researcher at ETH Zurich in the materials theory lab. Jonathan's work has been very key for us because he is one of the creators of the Alexandria database, which is a very carefully curated data set of DFT optimization trajectories, which was has played a big part in all of the models that have shown kind of over the last couple of years that have shown really strong performance on particularly the MATLAB discovery benchmark, but more generally kind of neural network potentials in general. It's a very high quality, consistent source of data, and I think he's going to talk about it now.
Yeah, thank you. Let's see. There we go. Yeah, I'm glad to hear that it's seems very consistent and carefully selected. I will talk more about this, especially about the trajectories that are kind of a side product. And I'm a postdoc in the materials theory group at ETH right now. And so we'll just start with thanking the respective people. So Nicholas Spalding and the group right now, who's paying me mostly to do other work. And then this is continuing kind of as a side project. And then we have Miguel Marx, who I've been working with before for, I think, around 7 years, and who runs all the DFT calculations, and I did all the machine learning roughly to arrive at where we are right now in terms of data. And then, of course, a lot of other collaborators who have been involved in various of the projects I'm going to mention. And then, of course, the supercomputing centers, without whom we couldn't do any of our work. So why are we doing this research? So if we look at the computers that we use now, like smartphones, we are claiming that we're in the age of the periodic table. So we don't only need silicon, but we need around 50 elements to build these computers. And so we also want to discover materials and use materials on these universal scales because, in terms of the periodic table, because else the technologies are not really possible. But of course, nowadays it's very important that what we're doing is also sustainable. And so this is one of our main motivations. We can look at the periodic table here from the European Chemical Society and see which elements are more or less sustainable. Some examples like cobalt and lithium have problems associated with them, but of course, essential for technologies like batteries that we're using right now. Now for cobalt, material science has already kind of, with lithium iron phosphate batteries, found an alternative, but not for lithium. And so for our research, the motivation number one was kind of to discover sustainable alternative compounds for current technology. And then, of course, we also want to discover new materials that enable new technologies. This could be anything from high DC superconductors that we have worked on a lot, some p-type transparent semiconductors, new permanent magnets, perovskite solar cells. And no matter, I mean, what technology we want in the end, all the crystal structures that have to, or that we can use have to be thermodynamically stable in the environment of application. And so when we talk about the Alexandria database, this has basically been accumulated over several years by looking for new thermodynamically stable materials. Now, what does that actually mean? Because I just introduced this concept. So we have something called the formation energy. So we will look at our elements. They will have some stable phase, and then we can say, okay, they have zero formation energy by definition. And when we make some binary phase where we mix two elements together, then usually, I mean, most of these phases will lie somewhere above already our elements. We can draw a line between them, and then the phase will decompose, and we will gain some energy through this decomposition. Now, of course, we can extend this concept of the formation energy, and then we arrive at what we call the convex hull. So if we have another stable binary phase down here with a certain fraction of our elements, then we can again draw these connecting lines. And now when we get the energy of, or obtain the energy of some new crystal structure, then most of them will lie above these lines, and these lines, what we call the convex hull, and then they will also most likely decompose at some point. And we can measure this by calculating the distance to this convex hull. Now, of course, I mean, we can do this also for ternary and quaternary and so on spaces, and it's just more difficult to plot. And so our goal is kind of finding new materials that lie below this convex hull and that will hopefully be synthesized. Well, now we know based on the existing experimental databases that, for example, most of the materials in the ICSD lie on the convex hull or pretty close to the convex hull. And so this distance to the convex hull is a good, I mean, or the best high throughput predictor that we have for synthesizability. Of course, then if one wants to go to experiments, it very much depends on the methods that one is using for synthesizing a material. And I mean, a lot more calculations and I mean, thought can go into this if we don't do it at the scale of, I mean, millions or billions of materials. And so the goal is basically to find these crystal structures. Now, in order to do that, we have to find a local energy minimum using some ab initio theory, and this is expensive. And we want to avoid doing that because we have to calculate the energies and forces a lot of times to find the local energy minimum. And then we can, I mean, put it in this diagram and evaluate the distance to the convex hull. Now, traditionally, people use something called prototype-based high throughput searches, which are kind of the lowest hanging fruits, where you can take an existing crystal structure like these perovskites here, and we can replace our elements here. So we have three elements, a ternary composition, with other elements from the periodic table, and we'll get maybe 500,000 combinations here for a ternary crystal structure. Now we actually, Now we actually did this in 2017 for these perovskites here, 250,000 calculations. And you can see here that we are actually mostly interested in these compounds here around zero. Sorry, I also don't have a pointer. And so our goal would be really that we only want to do, let's see. I'm not sure, are the slides changing for you?
Yes.
Okay, so which slide? Because for me, the slides are not changing anymore.
64.
64. And is this still the prototype-based high throughput search? No.
Graph networks for structural
Okay,
input.
so let me go. Am I back at prototype-based?
Yes.
Yeah.
Yes. Okay. Sorry. I think. Sorry. I think I have to reload this because the slide. So let me try to move. Is it still? No. It's. Sorry. I think I have to return because I cannot see the slides anymore.
Yeah. Okay.
So,
Okay.
yeah, now I can see the slides again. I just will I need the rights to continue
Yep.
presenting. Okay, perfect. Thank you. Yeah, so we really only want to calculate these 300 structures instead of 250,000. So we can actually research a lot of, find a lot of new materials. And so we want to avoid the rest of the 249,000 calculations. And now, a few years ago, when I think this was my bachelor thesis, basically at the time, we had like these super basic models where you could put in information about one prototype, about the composition. And already, with this like scikit-learn approach, you could reduce the number of calculations by around 80%. But of course, this only works for one prototype. And then we cannot scale with data or compute in any way because we need a new training set for every prototype. And so we need some models that are universal in terms of composition and prototypes. And this is where we get to graph neural networks, that we already had a little bit in the last talk. So we map our crystal structure to we map each atom to a node in our graph. And then, of course, depending on the distances between our atoms, we will have connection, and we'll have edges in the graph or we want. And usually in the edge embeddings, we put some distance expanded in a Gaussian or Bessel basis and maybe also some angular information. And this is kind of the problem if we want to do these high throughput searches, because if we want to do a single prediction to determine the stability, but we only have the unrelaxed prototype structure and not the relaxed crystal structure. And if one tries this with some graph neural networks, so these were, for example, improved crystal graph convolutional networks by Park et al., if we put in an unrelaxed prototype structure, and they obtained around 7 times higher errors in their prediction than putting in the relaxed crystal structure. And now this was before universal force fields existed. And so our idea at the time was what we can do is that we can replace this exact distance with some graph distance embedding. So we just say first neighbor, second neighbor, third neighbor, and so on. And then based on this information and using the attention mechanism and some, extra tricks in terms of scaling the models, the model will hopefully learn everything and we can make accurate predictions for relaxed crystal structures based on unrelaxed prototype crystal structures. Now, maybe in the context of the last talk, these networks also didn't contain any rotational equivariance. They're just completely invariant, but we also don't need forces and just energy. But of course, the point is here that we actually remove most of the physical information so we can have this coarse-grained representation where all the unrelaxed crystal structures kind of map to the same relaxed crystal structure. And so, at the time, in terms of data, there were some open database like the Materials Project that contained, quite high diversity in terms of crystal structures. And then there were some basically results from high throughput searches like the one we had done on perovskites, where for a single prototype, there would be kind of the whole periodic table. And so with these, we could pre-train our model, and then we could do some fine-tuning, maybe 1,000 or so structures from a specific prototype. And this allowed us now to do much larger unit cells like garnets, for example, with higher efficiency than before. Could do quaternary perovskites, so we are now for quaternary compound had around 40 million combinations. And so we'd always just predict all these combinations, calculate the most stable ones, fine-tune and repeat this process. And so we did this for around 20 prototypes and found around 4,000 new stable compounds in 400,000 calculations. At this point in time, so this was around 10% increase in the number of known thermodynamically stable compounds. But our model was still not universal because we still had to fine-tune. And so we needed more data. And so just to kind of illustrate the journey, we can look here at the distribution of our DFT validation calculations during these high throughput studies. So in 2017, we basically cannot see anything here. Oops, the scale is missing. And here, I think this should go up to 100 millielectron volt per atom distance to the convex hull. And now we have the percentage of stable compounds here. So here we have in the beginning 0.08% without machine learning, and then with some basic ML, and then the crystal graph attention networks, we could go up to 1%. And so over the last years, we have then done a lot of these calculations, and we just retrained our networks after several rounds. So first after these 400,000 compounds, then we did predictions for 1 billion ternary and binary compounds, doing around 500,000 calculations. And then our median distance to the convex hull was around 100 milli-electron-volt per atom. Now, the good thing is this was now data that was properly, distributed across the prototype and a space and the periodic table. And so retraining on this additional data, we were able to go down to around 70 milli-electron-volt per atom and do another 13 billion predictions. And in the next round, we were at around 50 milli-electron-volt per atom and did another, I think, around 4.5 billion predictions. And so this was kind of the last round that is already published. So here we're now at around 5.4% stable materials, and around 75% of the calculations we actually did for validation were below 100 milli-electron-volt per atom distance to the convex hull. And this also, the data set that is already available online. Now we have been combining some models and doing some substitutions recently, where we are now at around 96% below 100 milli-electron-volt per atom and 36% stable materials. So here we have we only did 40,000 calculations so far, but within these, in 2017, I think we would have taken around 18 million calculations to find these 14,000 new stable materials. Now, this was kind of the 3D space. In the Alexandria database, now we also have some 2D data. Just quickly going over that. So for 3D, we were quite lucky that a lot of prototypes are already known. But in the 2D monolayer space, we mostly had from Christian Tigerson, the C2DB database, and then from Nicola Mazzari. These were all materials that were found by computational exfoliation of existing layered compounds. And so with Aldo Romero and some other people, we developed an approach just based on some space group and our system dimensionality to create Wyckoff positions that we can randomly occupy with elements. And then based on some, basic chemistry rules, we can create some crystal structures that we can then optimize with DFT over the universal force fields at the time. And MagNet was, M3DNet was published as one of the first universal force fields for bulk. And then we can do DFT optimization, and in this way find a lot of interesting prototypes. Now, at the time, we also transfer learned some 3D MagNet to 2D, which was worked quite well, and we'll mention this later again. And then later on some Maze version. And for this, because the 3D networks have quite high errors if you use them in lower dimensions. So using this approach, we find a lot of new prototypes that are mostly nice to look at. They are also rather, stable. However, the problem is, of course, they are not based on this exfoliation approach. So it's not quite clear how we can synthesize them. But just to demonstrate, the importance also here. We have all the millions of 3D calculations, and then here we have distributions of some database. So this was the C2DB that we recalculated. There was the systematic approach, so without any machine learning, just doing calculations of randomly, based on symmetries, generated structures, and then transfer learning some crystal graph attention networks also to 2D. And we can significantly improve our distributions here and get much more stable crystal structures also in 2D. Okay, so all of this was then collected in the Alexandria database that's now hosted by Miguel March in Bochum. And it's accessible through the Optimate API and the Intel Labs Material Science Machine Learning Toolkit as well, and directly through the website. And we have around 4.5 million crystal structures. And in total, over the last years, we increased the convex hull from around 45,000 to 115,000 materials using crystal graph attention networks. Of course, there's also the Genome project by Google, who have, around, I would say, 3 times as many stable crystal structures, which are, of course, not, available under an open license. And then there are the 2D materials I mentioned. We also have some higher fidelity scan and PB soul calculations So we have also transfer learned some universal force fields on the PB soil trajectories. I would, of course, also be very interested in some higher quality, orb model, maybe, or something for PB. So if that would be something interesting, maybe. And what can we do with the data? On the one side, of course, we have material science, so we can select our materials close to stability. We can predict or calculate some property of interest, and then, discuss with our experimental colleagues about synthesizing them. So, for example, we have done some studies for superconductors, doing some machine learning predictions, and then electron-phonon coupling calculations for perovskites and anti-perovskites. We'll skip this. And then other applications that have been done already are, for example, rare earth-free permanent magnets or high refractive index materials. And of course, this can be applied quite universally. And basically, the database allows to skip a little bit the approach of trying to find first some new stable crystal structures. And there's just a large space of hundreds of thousands of materials that can be scanned for, the right properties. Now, the other direction is, of course, machine learning. So we have done some of our own benchmarks and trained some of our own models. I already mentioned some universal force fields for 2D. So here we have 3GNet and MACE evaluated on our 3D structures, 2D structures, and 1D structures that we also have. And so, we can see for 3D, MACE performed the best, and then followed, by the magnet and MACE 2D model. So the MACE 2D model was only trained on two-dimensional crystal structures and still performs similar to the M3GNet. And then we can see MACE generally transfers better to the other dimensions. And we can also see that the MACE 2D works still quite well in one dimensions, which makes me quite hopeful that if we mostly train on 3D data and add a little bit of two-dimensional, one-dimensional data, that we can perform well in all dimensions at once. Maybe this would also be very interesting in context of the equivariant versus non-equivariant models, how they transfer to the different dimensions. Now, some other applications on a larger scale. We had the MetaGen model by Microsoft, for example. So generative models for crystal structures, and they, developed a new architecture that allowed them to reduce their error in terms of, distance to the relaxed crystal structure by around factor 3.1. And then by adding data from Alexandria and ICSD, they were able to reduce it by another factor of 5.5. And of course, this data is freely available and everybody can make these improvements. And by now we have around 3 times as many structures available under the same criteria. And so there's huge potential for improvement there. Then, of course, we have the universal force fields. So we have the MERT bench discovery benchmark using also some subset of the Alexandria database that was created through substitutions. And here we have the MetaSim and the genome model from Google, that were trained on proprietary data sets, and neither the model or the data sets were ever published. And then we had the orb model here trained on the materials project trajectory data set. And then we can see the improvements through using the Alexandria database. It was, at the time then, the best performing model. And I was really happy to see this application because I never had the time and maybe also the skills to train this model. So this was great to see. And of course, since then, we've had the data set by Facebook and the OMA24 that was generated through rattling and running some molecular dynamics on structures sampled from the Alexandria database, and through, another, or let's say factor 3 more data, they were able to improve again. Now, maybe some words about this trajectory data set. So this was kind of a side product. So there are not, let's say, only for a certain percentage of structures in the Alexandria database, there actually the trajectories exist. And some of the trajectories also only contain one data point due to some corruption of the files where they were not properly written. on the supercomputing system, just as a note for people who try to use it. But I think Facebook, I mean, also with the OMA 24, published also a clean version of the trajectories. Yeah, then I think I'm doing on time. I will just skip this. So we had also PB, SOL, and scan data that, of course, can be used for transfer learning. But then in the interest of time, I'll just get to the end. And so all this data is available. If you have any questions, yeah, drop me an email or Miguel. And yeah, I'm quite excited about the future of the universal models. I mean, right now, for solids, we're a little bit lacking in benchmarks, maybe because the mud-bench discovery is kind of, I mean, getting, or let's say we are close, I mean, more than above 90%, and I think it will be quite difficult to see like valid improvements that actually transfer into practice. But I've seen there already some new additions in terms of modeling of thermal conductivity and so on. But I think there are some new benchmarks will be very important. Then, of course, we need some higher fidelity data. And of course, I'm also quite excited about, I mean, the diffusion and denoising based self-supervised training approaches to make more use of the existing data. Okay, thank you very much. And I hope you can find some use in the data.
Great. Thanks, Jonathan. Cool. So we've already got some questions. So are you calculating the phase diagram, or is the phase diagram already known? If so, how is it used?
So yes, so we, I mean, for each crystal structure that we calculate, I mean, so we directly predict the distance to the convex hull, and then if the material is close to stability, we calculate the phase diagram in the, I mean, concept of the convex hull. I mean, based on all the structures in our database that are stable. And so, I mean, then, I mean, this information is mostly used for high throughput searches, like for the superconductors and so on. And then there may be also some more advanced methods to make use of this knowledge of this phase diagram, like Christine Persons' group, for example, is working on this direction.
Nice. Rayan is asking which part is the biggest bottleneck for the model in terms of computational time or cost, but I guess also I'll be interested in the computational like costs overall. Like, were you finding that the main limiting factor here is the density functional theory that you're running, or the rounds of kind of model prediction that you do?
Yeah. Do you have some slide? Let me check. No, I don't have a slide on this right now. I mean, the DFT is always the limiting factor, and it's much more expensive. So I mean, but this comes actually, I mean, it's a little bit a problem. So with the we're still, I mean, even when the first generation of universal force fields came out, we were not using them for this, because even though they were, I mean, on the same level of performance or slightly better than the CGATs, I mean, we have to do relaxations, which are very slow, while with the CGATs, we can do batch predictions of thousands of materials at once on a GPU. Yep. And so they were like, I mean, several orders of magnitude faster than doing it with universal force fields. But then, I mean, we can do thousands of predictions each second on a GPU. And so the DFT is by far the limiting factor.
Nice. Sachin is asking how you calculate the thermodynamic stability after getting the decomposed compounds through your models. I'm not quite sure.
Yeah, I think so. I mean, with the CGATs, we were directly training on the distance to the convex hull, because, I mean, for billions of compounds, calculating the distance to the convex hull would also take forever. Right. And we're directly predicting it. And I would not recommend to use the distance to the convex hull on more than 5 element systems in general, just because entropy plays such a large role that, yeah, I mean, that just the knowledge of the distance to the convex hull, I don't think is sufficient. Let's say it like this. I don't think we have, I'm sure maybe there were a few compounds with more than 5 elements in the training data, but we have only ever done predictions for quaternary compounds because everything beyond that, we get too much into the entropy regime. And I mean, already for quaternary compounds, this order is important.
Nice. I think I'm going to redirect Bharat's question to either some of the Matheson papers or our paper on pre-training using diffusion models. So let's jump to Johannes's question. So magnetic potential is notoriously difficult because of sampling the large space of spin configurations. What advancements do you see in there in the kind of near future?
So this is a mixture. I mean, I would say that 70% of the challenge there's on the electronic structure side, in terms of single calculation parameters. I mean, not working well for all magnetism, and magnetism is not equal to magnetism. So we have all kinds of different physics there that once we have good data, of course, we can model with a single model. So I'm not worried about that. But right now we don't have a DFT approach that consistently works for all magnetic materials. And so there we'll have to mix a lot of data from different sources. And then some, I mean, of course, some kind of, strongly correlated materials are difficult to produce good data on anyway with DFT. And then, it's a mixture of making the models more efficient, and denoising and so on are great for that, and self-supervised approaches, I think. And then, of course, it's about putting in the hundreds of millions of hours of compute time again to extend data sets.
Yeah. This is a question I'm kind of interested in. Can the models be extended to, well, Ritika is asking amorphous polymers, but in general, other materials classes? Or is there something very specific about the kind of data you started out with here that?
So, I'm not. Yeah. There are certain, concepts, synthesizability, I guess, I would generally say no. What we're doing doesn't really work. Graph attention networks, I think, are basically used everywhere. So I guess that, concept is already used, kind of universally. But besides that, to my understanding, the other concepts don't really work. So in terms of, data and approaches, no, I think it's a completely different problem.
Right. Nice. Do we have any other questions? Otherwise, I think we can probably wrap up. So we've run over slightly, but good to get questions for both Marcel and Jonathan. So thanks for joining, and thanks to Marcel and Jonathan for presenting.